Right now, as you are watching this, NOAA's Space Weather Prediction Center has just issued a fresh geomagnetic storm watch, warning that conditions could reach G2 or moderate on the 2nd of August with the greater than 2 million electron-volt electron flux at geosynchronous orbit. The exact measurement satellite operators watch most closely, expected to spike to high levels on that same date. That alert would not normally be remarkable on its own, but it is arriving during one of the most active stretches this solar cycle has produced in months. A run in which the sun has already beaten official forecasts twice in less than a month, once by a full 2 storm levels. This is the story of the space weather threat currently building toward Earth, why forecasters keep getting surprised by how strong these storms actually turn out to be, and what that unpredictability could mean if one of these events turns out bigger than expected. No hype, no exaggeration, just what the data says and why it matters. Drop a comment and tell me if you have ever actually seen the aurora where you live. I read every one of these. If you want grounded science coverage instead of panic headlines, subscribe. It is free, and a like helps this reach more people before the next alert comes in. Let us go for 5,000 likes on this one. Thank you. Now let us get into it. To understand why this particular stretch of space weather has forecasters paying closer attention than usual, you need to understand the basic mechanics of what actually causes a geomagnetic storm. The sun periodically ejects enormous clouds of magnetized plasma called coronal mass ejections, or CMEs, out into space. When one of those clouds is aimed at Earth and eventually slams into our planet's magnetic field, it can trigger a geomagnetic storm, and NOAA ranks the severity of those storms on a scale from G1 or minor up to G5 or extreme. But here's the part that makes this genuinely difficult to forecast with real precision. The intensity of any given storm depends almost entirely on a single, hard-to-measure property called the Bow-Lizzy component, the north-south orientation O, if the magnetic field embedded inside the incoming CME itself. If that field points strongly southward when it reaches Earth, it undergoes something called magnetic reconnection with our planet's own magnetic field, effectively opening a door that lets solar wind energy flood directly into the magnetosphere and drive an intense storm. If the field points northward instead, Earth's magnetic shield largely deflects the incoming plasma, and the same CME barely produces a ripple. The problem is that Bow-Lizzy cannot actually be measured until the CME reaches a satellite called Solar 1, positioned at a gravitationally stable point called Lagrange Point 1, roughly 1.5 million kilometers, or 930,000 miles sunward of Earth. That satellite gives forecasters only 15 to 60 minutes of confirmed warning before the storm's real effects begin, meaning every forecast issued more than an hour in advance is fundamentally a probability estimate, not a confirmed reading. That single limitation is exactly why this particular stretch of solar activity has already produced 2 forecast surprises in the space of a month. On the 4th of July, a CME struck Earth and rapidly intensified into a G3 or strong geomagnetic storm, arriving 2 full levels stronger than NOAA's own pre-arrival forecast had projected, lighting up the aurora across 30 separate United States, far further south than a typical storm of that strength usually reaches. Just weeks before that, on the 8th of June, a separate CME merged with another one already in transit and struck Earth as another G3 storm, driving visible aurora as far away as France and New Zealand simultaneously, a genuinely unusual spread for a single storm. Both of those events shared the same underlying cause, and it is the same mechanism. Forecasters are watching for again right now. That mechanism is called a cannibal CME. When a faster-moving cloud of solar plasma catches up to and physically overtakes a slower CME still traveling through space ahead of it, the two do not just pass through each other, they merge into a single, denser structure. Researchers call complex ejecta, carrying more combined magnetic energy than either individual cloud would have delivered on its own. The historical record backs up just how consequential this kind of merging can be. The Carrington event of 1859, still the benchmark for the most extreme space weather event ever recorded, involved several successive solar eruptions arriving close together and produced aurora visible at unusually low latitudes for 4 consecutive nights. The critical problem with a cannibal CME, though, is not just that it carries more energy, it is that the merged structure's internal magnetic field becomes significantly harder to model and predict, because you are effectively trying to forecast the combined, tangled magnetic orientation of 2 separate eruptions that were never supposed to interact with each other in the first place. A cannibal CME arriving with a strongly southward Bow-Lizzy during a week when multiple sunspot regions on the sun are still actively producing new eruptions is exactly the scenario that produces a storm, capable of exceeding NOAA's forecast, precisely the way the 4th of July event did. That is essentially the exact situation building right now. Over the final days of July, The sun produced a wave of solar filament eruptions and coronal mass ejections in fairly rapid succession. A large eruption on the 24th of July, launched from an active region on the sun's southern hemisphere, reached Earth's magnetosphere late on the 26th and produced G1 to G2 conditions on the 27th. But NOAA's forecasters were explicit that this was not the main event of the week, describing that CME as weak and flanking, meaning a glancing blow rather than a direct hit. The more significant threat came from a follow-on wave. Additional CMEs launched around the 27th and 28th of July that were expected to merge in transit through the classic cannibal CME process and arrive with G2 to G3. Strong conditions by the following Wednesday. At G3, power grid operators at high latitudes begin facing real physical risk. Geomagnetically induced currents strong enough to saturate the cores of electrical transformers, a level of impact well beyond the aurora, watching most people associate with a solar storm. Behind all of this sits a solar disk that remains genuinely more active than the sun's overall. Declining trend would suggest it should be. NASA and NOAA confirmed back in October of 2024 that the sun had reached solar maximum, and the smooth long-term sunspot count actually peaked around the 11th and 12th of October that same year, with a real, measurable decline in overall activity becoming visible by February of this year. Despite that broader decline, the Earth-facing side of the sun currently hosts multiple sunspot regions with significant internal magnetic complexity. One region, cataloged as AR4494, carries what solar physicists call a beta-delta classification, the single most energetically complex magnetic configuration a sunspot group can have, and it continued showing new magnetic flux emerging as recently as the 26th of July, a sign the region is still actively building toward further eruptions rather than winding down. A newer region, AR4496, growing in the sun's northeast quadrant, is described by researchers as having many more days of what they call geo-effective potential ahead of it, meaning its position and orientation still favor firing material directly at Earth as it continues rotating across the visible solar disk. Another nearby region, AR4492, produced an M-class flare, one tier below the most powerful X-class eruptions, on the 30th of July, just before rotating out of Earth's direct view around the sun's western edge. Space weather researchers now describe the period running through approximately the middle of 2027 as a window of sustained elevated risk for satellite infrastructure and high-latitude power grids specifically, because this declining phase of the current solar cycle has remained significantly more active than the equivalent quiet years, 2019 and 2020, were during the previous cycle. Here's the comparison that shows what a genuinely worst-case version of this pattern actually looks like, because it already happened once during the same solar cycle. Between the 7th and 11th of May in 2024, a cluster of X-class solar flares combined with multiple coronal mass ejections to produce one of the strongest geomagnetic storms of the entire 21st century, rated G5 extreme on NOAA's scale. That event produced widespread aurora, visible across North America, Europe, and parts of Australia simultaneously, disrupted satellite communications, and pushed radiation levels high enough that operators reported real measurable effects rather than just a photogenic sky. Just months later, in October of that same year, a separate G4, severe, storm followed a fast-moving CME traveling at speeds between roughly 1,200 and 1,300 kilometers per second, producing a geomagnetic disturbance measurement called the DST index of approximately negative 340s, 1 nanoteslas, one of the most intense single storms recorded that entire year. Compared to those two events, the current watch for G2 to G3 conditions is considerably more modest, but the underlying mechanism connecting all of them, multiple eruptions from magnetically complex sunspot regions merging together during transit, is the exact same process, just operating at a smaller scale for now. So what does all of this actually mean for you? For the overwhelming majority of people, a G2 or even G3 geomagnetic storm poses essentially no direct danger and represents, at most, a genuine opportunity to see the aurora somewhere it does not normally reach, potentially as far south as the northern tier, the United States, southern Canada, Scotland, and Scandinavia, depending on exactly how the bee's orientation behaves once the CME actually arrives. Commercial flights remain safe to fly during storms at this level. Astronauts aboard the International Space Station remain shielded by Earth's own magnetosphere for the vast majority of their orbit, and the average smartphone or car GPS will see only marginal temporary accuracy degradation at worst. The real audience for a genuine concern is a narrower one, high-latitude power grid operators watching for geomagnetically induced currents, satellite operators tracking increased atmospheric drag on spacecraft in low Earth orbit, and aviation authorities monitoring high-frequency radio degradation along polar flight routes. What this specific stretch of activity demonstrates clearly, though, is that the gap between what forecasters predict and what actually arrives can be significant, up to 2 full storm levels in the case of the 4th of July event, and that gap is largest precisely during periods like this one, when multiple active, magnetically complex sunspot regions are firing eruptions in close succession, exactly the ingredients for the cannibal CME merging that keeps catching forecasts off guard. So here is the honest, grounded summary. The sun remains meaningfully more active than the overall decline of the current solar cycle would suggest, driven by a cluster of magnetically complex sunspot regions, including one carrying the most complex classification a sunspot group can have, that are still producing new eruptions as they rotate across the visible solar disk. That activity has already produced 2 forecast-beating storms within the past month, and NOAA has now issued a fresh watch for renewed G2, potentially G3, conditions arriving in the coming days, driven by the same cannibal CME merging mechanism responsible for both of those earlier surprises. None of this approaches the scale of 2024's genuinely extreme G5 storm, but the underlying process building it right now is identical, and forecasters are being explicit that the true intensity of whatever arrives will not be confirmed until roughly an hour before it actually hits. We will keep tracking this the same way we did today, straight from NOAA's space. Weather Prediction Center, NASA Goddard's heliophysics researchers, and the solar physicists actually monitoring these active regions, not recycled headlines. Subscribe so you do not miss the next watch, because based on what we just walked through, the sun is not finished yet. And leave that comment below. Tell me whether you would actually go outside to try to catch a glimpse of this if it reached your area. Because behind every one of these alerts is a power grid operator somewhere at high latitude, checking transformer readings in real time, a satellite engineer watching for a sudden spike in atmospheric drag, and a research satellite 1. And 500,000 kilometers from Earth, right now, quietly measuring the one number that will decide whether the next few days bring a spectacular light show or something far more disruptive. 5,000 likes on this one. Let us go. See you in the next one.